Hi everyone, I am Georgina, professor and researcher of the Faculty of Physical and Mathematical Sciences of the Benemérita Universidad Autónoma de Puebla in Mexico, and I am honored to present you this work. The work is titled A Comparative Study Between PCR and PLSR in a Tapered Optical Fiber Sensor for Acetone Detection. The use of multivariate analysis techniques and prediction models represents a novel alternative in sensors based on optical fibers, since they have a great potential to estimate the properties and quality of the response of optical fiber sensors. This work focuses on comparing and determining the accuracy of prediction models such as multivariate projection to latent structures regression, PLSR, and principal components regression (PCR) techniques applied to tapered optical fiber sensors, as well as experimental studies of the different sensing films used, such as PDMS, PMMI, APT, and APL for acetone detection. Multivariate analysis methods such as PLSR and PCR are a good alternative to be used in optical fiber sensors since they allow taking advantage of all the information obtained from the experimental spectra, analyzing the complete spectral range that is being measured and that determines the behavior of the sensors. Optical fiber sensors have become a great alternative due to their advantage, such as high sensitivity, immunity to electromagnetic interference, simple manufacturing, and faster diagnosis than other methods. These sensors can monitor different physical and chemical variables, as well as measure a wide variety of volatile organic compounds, of which one the most important to measure is acetone, since it is a biomarker for detection of diabetes mellitus. According to reports from the International Diabetes Federation, 10.5% of adult population between 20 to 79 years has diabetes, and it is projected to increase by 46% by 2045. The diagnosis of the diabetes is usually made by invasive methods. However, the relationship of blood glucose and breath acetone concentrations opens an alternative to a new detection method. Reported breath acetone concentrations are 0.044 to 2.744 ppm in healthy patients and 1.76 to 21 ppm in diabetic patients. In this work, we proposed the experimental study of a tapered fiber or TOF sensor. In addition, we introduced different sensing films such as PDMS, PMMA, APT, and APL that interact with the TOF and allow to detect low acetone concentrations. A comparative study of acetone concentrations response sensor predictions model has performed used multivariate analysis techniques such as PCA, PCR, and PLSR. The results show that using 4 components in our predictions, PLSR gave the best LOD, which was 5.56 ppm for the sensor with PMMA sensing film, which is an improvement of the performance of TOF sensors. In this work, we used 3 analysis methods. The first, it was principal components analysis. This method is a multivariate statistical method that reduces a data set to their essential characteristics. This method provides an approximation of the original data set using only a few major components. The next method was principal components regression and is a statistical technique for regression analysis. PCR uses as predictors in linear regression the PCs or principal components obtained with PCA in order to give more reliable estimates. Finally, the last method used in this work was projection to latent structure regression or PLSR, and this method is a transformer and a regressor. It's quite similar to PC, however, is a more prediction-oriented method than PCR, since the later reduce the dimensionality of the input variables without considering the relationship between the input and output variables. For each sensor, an 18 centimeters long optical fiber was used and it was submerged in hydrofluoric acid for a diameter reduction. And the chemical reagents used as sensing films were PDMS, PMMA, APT, and APL. And finally, the biomarker used was acetone. All reagents used were of analytical grade. The figure 4 shows the output transmission spectrum of each sensor and its variations under the effects of acetone concentration changes over a range from 1,400 nanometers to 1,515 nanometers. The spectral variations were not perceptible, therefore were performed as zoom in the peak of the spectrum, which allow us to visualize the spectral changes for each concentration. In general, the maximum amplitude variations were perceptible around 1,475 nanometers, and these variations can be interpreted as changes in the refractive index due to the interaction of the sensing films with acetone molecules. However, these variations are quite small. It's still possible to use the traditional demodulation technique, which is based on the measurement of the shift and or attenuation of the spectrum in a specific wavelength. However, this will cause waste of information since we can take advantage of the complete spectrum information using a multivariate analysis like PCA, PCR, and PLSR. Each spectrum contains 751 measurements in different wavelengths, which implies 751 different predictions of the acetone concentrations. This number can be reduced to only 2 or 3, maximum 4 components by using PCA and PLSR, and the results with 2 principal components of the sensors with the respective sensing films for different acetone concentrations are shown in figure 5. The measurements were taken every minute for a period of 10 minutes of each acetone concentration, and for the PCA analysis, the data were taken from the 10th minute of each concentration. In this figure, we can observe a general trend where the concentrations increase from positive to negative values for PC1, while it increased from negative to positive values for PC2. In the case of PDMS, only has a response up to 498 ppm that are injected. For the following concentrations, there is an abrupt change in the behavior where it is not clear to observe that the components follow a well-defined trajectory because their values seems to change randomly. On the other hand, For PMMA, this behavior is still worse since the data seems not to follow any trend in both PCs, which will indicate that the sensor has no response for any concentrations. However, as we will show later, using more components, it is possible to show that the sensor has a response using other techniques as PCR and PLSR. It is possible to improve the sensor response evaluation. In the case of greases, APT and APL presents a clear response. Is even better since the response follow a linear behavior for the complete range of measured concentrations in the PC's space. Figure 6 shows the sensor responses for three principal components with PCA, and from here we can notice that the four sensors follow a general trend on acetone concentrations. It is possible to discriminate the response for each sensing film since they do not overlap between them. On the other hand, as the acetone concentrations increase, in PC1 the data moves from negative to positive as well as in PC2, while for PC3 the data moves downwards. It is important to mention that the behavior of the sensors with PMMA for three components, unlike the analysis with two, presents a clearer trend for acetone concentrations. If one more component was added, we could observe an even clearer trend. However, it is not possible to plot four or more dimensions. Through using PCR and PLSR, we can determine the sensor response behavior in function of a larger number of components. The same comparison was also performed with PCR and PLSR using four components. For these regressions, PLSR is even closer to the experimental data compared to the case of PCR, and the difference between both models is also more evident for all the sensors. In the table 2, the LODs achieved with PCR and PLSR for 1, 3, and 4 components. With PCR, the results show that the best response was obtained with the PDMS sensor, reaching a LOD of 63.24 ppm with 3 components and 62.94 ppm with 4 components. On the other hand, with PLSR, the best response was obtained with the PMMA sensor, reaching an LOD of 5.56 ppm using 4 components. Finally, in the figure 10, the LOD in function of the number of the components using PCR and PLSR is shown. In general, the values for the case of PLSR are lower, and in both techniques, they decrease as the number of components increase. The improvement in PCR is evident from changing from 1 to 3 components, and after that, it is negligible, especially in the case of PDMS and PMMA. On the other hand, in the case of PLSR, the improvement is quite regular for all the sensing films. In this work, a comparison of the multivariate analysis techniques, PCR and PLSR, was performed to improve the performance of four sensors constructed using a tough configuration and using different sensing films such as PDMS, PMMA, APL, and APT. The sensors were used for the detection of acetone, a biomarker of diabetes mellitus, in the measurement range from 33.2 ppm to 1826 ppm. We used PCA as a first approach. In PC1 versus PC2, we observed response strengths in function of the acetone concentration, except for PMMA that seemed not to follow any trend. However, for three PCs, a clear trend was observed. To improve the analysis and using the whole concentrations range measured, PCR and PLSR were performed, and the performance of both methods was compared. In general, PLSR performs better than PCR using the same number of components. The best LOD obtained using PCR was 62.94 ppm for PDMS and 4 PCs. On the other hand, the lowest LOD was 5.56 ppm obtained with PLSR and 4 LS or Latin structures for PMMA. PLSR, by taking into account the input and output variables, allows a considerable improvement in the analysis of the sensor response, which allows us to analyze sensors even with an irregular response.